afternoon session. So our first speaker is Prakash Hayden. So please.
All right, so I'm going to speak about some work that started a couple of years ago and has continued since then. It's with some students, Alex May, Sefer Nizami, and Grant Salton. And it's about how quantum information can be distributed in space-time. Now, sitting in the audience this morning, I've become very aware of what a truly, I'd always known that Prakash had wide-ranging interests, but when you actually see his collaborators and friends speaking on such a wide range of topics, it really drives home the fact that that is true. So I'm going to make it at least some attempt for this talk to be accessible, and for that reason I have to apologize to Prakash, because I know that he's studied this and he knows most of it, but the reason I chose it as a topic is for what's going to appear in the last 5 minutes, which is new stuff. And I know that any time some interesting mathematics appears in an unexpected context, that gets Prakash excited. And so that's the reason for the selection. I'm going to begin with a poem, actually written by my wife yesterday, who also considers Prakash a great friend. So we gather to honor Prakash Panangaden, a scientist, mentor, and friend ne'er forgotten, who inspires us all with curiosity untamed. Each year finds him mastering a whole new domain. From programming languages to emissions stimulated, he's figured out functors and black holes illuminated. An expert in logic and probability, he's also quite fluent in concurrency. A professor universally esteemed by his peers, he strikes the right balance between beloved and fear. For students who think they can get by half-assed, his rigorous demands prove a hair-raising blast. We can't categorize him, he's too multidimensional, but we can testify his curry's sensational. Of our Royal Society, he's a fellow for life, though we will note he got in only after his wife. How fitting it is to hold this celebration in a place steeped in centuries of innovation, from Haley to Hardy and many fine chaps, inspired by science and by some pork perhaps. To Prakash on his 60th, let our cheers resound. A finer colleague cannot be found. When I just said. All right, so now on to this quantum information story. You don't need to know too much about quantum information, or at least hopefully not for this talk. But one thing that you should really know is that quantum information cannot be copied. We say that quantum information cannot be cloned. And what that means is that if you have some quantum system, and it's in a state, but you don't know what that state is, so imagine you have an atom, and you want to copy the state of the atom. You want to prepare two atoms in exactly the same state as the one you started with, you should give up. That's something that can't be done. So the way this is drawn here, the state of a quantum system, there is no physical process that will take you to two copies of the same state if you don't know what it was in advance. We could also phrase this as just saying that quantum information cannot be replicated in space. Good enough. And yet, if I draw a space-time diagram, so here my space is on the horizontal axis, time is on the vertical axis, and I imagine again that atom is sitting at the at this point here and then follows some trajectory in space-time. There's what we call its world line as it moves around. Then that same quantum information is going to, of course, travel around with the atom. And it's going to get copied. It's here, and it's there, and it's there, and it's there. And so it's at many points in space-time, even though we can't put it in many points in space. And so while quantum information, because it cannot be copied, as I described before, cannot be replicated in space, it has to be widely replicated in space-time. Because the laws of physics, the transformation that takes you from one time to the next is reversible. It's a unitary transformation on a vector space. And so it has to be copied from one time to the next. And what I'm going to tell you about is a precise characterization of essentially all the different ways that it can be replicated. And if the story was just very simple, like what I drew right here, this it's carried along trajectories, this would be a boring talk. And so there's going to be a more interesting story to tell. So first of all, to understand the inadequacy of trajectories, it's helpful to just know a few basic facts about quantum information. And there's this procedure discovered more than 20 years ago now called teleportation, which is a way of getting quantum information from one location to another. And so here we have, again, imagine it's an atom or something like that, and you want to transfer the state to another location. If you try to measure the state, you're going to damage it. right? So you can't just measure it, get on the phone, and tell your friends what the state is. But if you happen to have interacted with a system held by your friend in the past in such a way that the two systems are correlated in a particular quantum mechanical way, we say that they're entangled, then you could jointly measure your half of the entangled system and the state of the system that you want to send, and then communicate the outcome of that measurement over the telephone. Once your friend receives the information that you transmitted over the phone, they do a little fix-up, and out is going to come a system in the state that you intended. And so you can get the quantum information from one location to another, but you might ask, well, did it travel along this causal trajectory when you got on the phone and communicated? Because that's the only sort of, well, the only communication that takes place in this problem. Or did it somehow travel backwards in time through that interaction? Because that's where the quantum mechanical stuff is going on. And the basic story is that I think neither of those descriptions is really an adequate story of what's going on, and that we need some other way of thinking about this. Another example of a situation that, again, is perhaps a little bit perplexing that one would want to be able to think about is the phenomenon of topological order in quantum mechanical systems. And all one really needs to know about there is that there are systems with, say, with degenerate ground states. The degeneracy, so the number of states, the dimension of the space of ground states, depends in some way on the topology in which you've actually, the topology of the system. And in these systems, what you can have is a situation where the information is robust to local corruption. It can be naturally resistant to damage. And when you think about how the information then has to be replicated, or how it has to be stored, it's going to be stored somehow in multiple overlapping subsystems of your material or whatnot. And so somehow you can actually have information which is not located in a specific place, but is located in a distributed way in some medium. And so we want to be able to talk about that as well. And so the outline of this talk is just going to be, first I'll define the problem. What do I mean by replicating information? I'll actually show just a very simple example, and then give you the complete characterization. And the complete characterization of what is possible is going to depend on the existence of certain kinds of quantum error correcting codes. So I'm going to tell you what that means. And then the little bit that's new for Prakash is that we would actually like to convince someone who does quantum optics, who does experiments, to demonstrate such a thing. And it's much easier to do it with continuous variable quantum information, a state of an optical mode, for example, than with the qubits that people normally talk about. And so we have to talk about some new kinds of quantum error correcting codes. All right, so we want to think about replicating information in space and time. And so we have to think about, well, how is the information going to be localized to a particular region of space-time? We're going to talk about localizing that information in what we call causal diamonds. And so the causal diamond is going to be identified by 2 points in space-time. So a base point, which I'll call my y naught here, say, and an apex, z naught. And the causal diamond is going to be the intersection of the future of the y, so everything in its future light cone, and the past of the z. Right? So it consists of all points that can both be affected by something that happens at y, and can affect what happens at z. Right? So that's this causal diamond. And we're going to be interested in the question of whether or not we can localize some quantum information, in this case, say both to diamonds d0 and d1. Is that something that could ever happen? And in fact, just to get you oriented, this is something that can happen, and it's totally uninteresting. Right? That if, again, imagine we have I'll say an atom, we should probably think more of a spin. If you're a physicist, that'll make more sense to you. But we could localize some information and carry it along a trajectory here in space-time into d0, and then just change direction and have it move over into d1. And so that same information is going to be in both diamonds. Right? That's uninteresting. And I guess the only point here that I should drive home when I'm speaking about space-time, the way that particles can move is governed by relativistic causality. And so nothing can travel faster than the speed of light, and in my diagrams here what that means is that all of these trajectories have to move with a slope of at least 45 degrees. Right? Okay. And so for the case of 2 diamonds that I've just been describing, we've actually, you may not have noticed it because we haven't done anything yet, but we've actually essentially completely analyzed the situation. that if there is some way to send a signal from one of the diamonds to the other, then this replication task is possible, right? Because you just move the information along that causal trajectory. On the other hand, if there is no way to send a message, either from diamond 0 to diamond 1, or from diamond 1 to diamond 0, then these two diamonds are space-like separated. And to succeed at the task would be to succeed at this copying of information, right? Because you'd have the same information at in two space-like separated regions, which is a violation of this principle that I told you on the first slide, right? The no cloning principle of quantum mechanics. And so that's the whole story in the case of the two diamonds. Right, and I should just introduce a little bit of vocabulary. I'll say the two diamonds are causally related if there's a way to, if there's a causal curve, there's essentially a way to send a message from one diamond to the other. And I don't care whether it's from diamond D0 to D1 or from D1 to D0, right? But I'll just use the term causally related. And now a little bit of causal diamond geometry. So here's one of my diamonds. I can foliate this diamond by space-like surfaces. And the quantum mechanical time evolution from one surface to the other is unitary, it's reversible. And what that means morally is that if the information is inside the diamond, it has to be on one of these space-like slices inside the diamond. And if it's on one of them, because the time evolution from one to the other is unitary and therefore reversible, it's on all of them, right? And so I've been speaking about localizing information in these diamonds, which you may have a little bit of difficulty conceptualizing if you're not used to thinking in these terms. And so it's helpful to think, well, what does one of these slices look like? And if I intersect, a cone, the future cone with the past cone, and just the surfaces of those cones, where do they intersect? They intersect in a sphere, right? And so one of these space-like slices, the one at the waist, actually just looks like a sphere. And so instead of talking about localizing information in a causal diamond, if you wanted, we could just say that we're localizing the information in a particular sphere at a particular time, right? So the simplest notion of localization of information that you could talk about, with the caveat that I don't really require that this apex point have the same coordinate, spatial coordinate, as the base point, right? So my diamonds can actually be kind of skew diamonds, like I've just drawn right here. And if they're skew, then that waist, it looks like a sphere to an observer, an inertial observer who's passing through these 2 points, right? But it may not look like a sphere to somebody who's not in that same reference frame, okay? Now a little bit more causal diamond geometry, as you were just seeing in the previous slide. As I move this apex point closer and closer to the edge of the future light cone, at least in the coordinates that I've drawn here, this diamond gets flatter and flatter until it degenerates into a line segment when I move the apex point onto the light ray. And in the diagrams that I'm going to draw from here, all of my causal diamonds are going to look like these degenerate causal diamonds. They're going to look like line segments. What you should keep in mind is that they're not actually line segments. They have some finite width, just, it's a finite small width relative to all the other scales. And the only reason I do that is because the pictures look simpler, and I'm not a great artist. And they'll be complicated enough as it is. Okay. So you need to know a little something about quantum error correcting codes, but not very much here. I guess maybe, again, since there are a lot of people who don't do quantum information in the audience, I should just tell you why the whole phenomenon of something like quantum error correcting codes are interesting. You're computer scientists, so you've probably encountered error correcting codes of some kind or another. Now quantum states are vectors in a complex Hilbert space. So you might have thought there'd be no way to correct those things anyways, because it's not discrete. It turns out that's not a problem. You might also have thought, by virtue of this no cloning statement that I told you earlier, that would prevent you from achieving the kind of redundancy required in order to get robust error correcting codes. It turns out that's also not a problem. But these are all kind of miraculous facts. Here's an example which will be useful to us, which is just how you encode a quantum system with 3 distinguishable states. In jargon, we'll call it a spin-1 system, into 3 such systems. And so what that means is that there's going to be one of these quantum systems with 3 distinguishable states, and we don't know what that state is, but then the 2 other such systems, we're going to prepare them in known states. And then we're going to allow them to all interact with each other in a controlled way for some particular amount of time, and something's going to come out. And what's going to come out is going to have the property that if you collect any 2 of the, I'm going to use the word atoms here, just for the members of the audience who want something concrete, even though that's really a little bit misleading. Say we collect 2 out of the 3 atoms, it doesn't matter which ones, that's going to be enough to reconstruct the information. So despite the fact that we don't know which of the 3 actually contained our information, that's going to work for us. So for classical data, you could do something like this easily with a repetition code, for example. But in the quantum case, again, you should think of these being vectors in a complex Hilbert space. It's kind of a non-trivial fact that it can be done. And if you're curious about how it happens, here is the state of my system coming in. It's a vector in a complex Hilbert space. This is just our funny notation for vectors. I've just expanded into basis. And the state space of 3 such things is the tensor product of 3 individual state spaces. And this is what the encoded state would look like. But we can, the bottom line is we can do this. There is a way to encode quantum information, the quantum information of some system into 3 systems, such that collecting any 2 out of the 3 shares is sufficient to recover the state of what I started with. Okay, so now let's do a non-trivial case of this replicating quantum information in space-time. So here's what I call the causal merry-go-round. Now in this picture, the aspect ratio is a little bit off, but what you should think about what it's supposed to show is an equilateral triangle. The y's are supposed to form an equilateral triangle in space. So I have 2 spatial dimensions, and the vertical direction is time. And then the z's also form an equilateral triangle, but on the midpoints of the edges between the y's, and translated in time. And the translation in time is precisely long enough for a message to get halfway between the y's. Right? So if I point a laser from y0 in the direction of y2, then the displacement in time is just long enough for the light ray to get halfway from y0 to y2. Okay? So that's the geometry here. And my causal diamonds, I have 3 of them. I have the y0, z0, so each black line segment is a causal diamond. I have the y1, z1, and the y2, z2. And the black rays are light-like line segments, right? So they're line segments along trajectories that light would follow. And because I displaced the z's from the y's, or the time displacement is just half the amount of time required for a message to get between the y's, these red rays are also light-like directions. So that's my geometry here. And we want to ask the question, can the same quantum mechanical information, this uncopyable stuff, appear in all 3 of the black line segments? And if you look at this, you might think, well, okay, let's start off with our quantum information down here, think of it as an atom or something, and we send it to y2. This red ray is a light-like trajectory, so it's causal. I could have my particle, if it were massless, follow that ray up to z1, and then I'd have the information in both the 2 diamond and the 1 diamond, right? But then we'd be sunk, right? Because from z1, there's no way to get to the 0 diamond without going backwards in time, right? Without doing something that is acausal. I'd have to hop across from z1 to z0 instantaneously. And that cannot be done. That's a violation of the laws of physics. And so it looks like this is not going to happen. However, we can be more clever, right? So we can take this information and we can encode it into one of these 2-3 threshold quantum error correcting codes. So what does that mean? It means that the information, I take it and I encode it into 3 shares, 3 separate particles now, with the property that if I can collect any 2 out of the 3 particles, that's enough to reconstruct the quantum information. And I'll send one of those particles each to each of the y's. And then those particles are going to follow the red trajectories, like so. And you may have missed it, but we just succeeded in replicating the quantum information in all three of the diamonds. So let's go back and make sure that it happened. So at this later time, each of the diamonds contains 3 particles, right? Oops. At the earlier time, each of the diamonds contains 3 particles. Or so each of the diamonds contains one particle, and at the later time, each diamond contained 1 particle. But if you look, say the particle in the 2 diamond, for example, in the early time, is not the same particle as at the late time. And so the 2 diamond contains 2 particles. And that's enough to reconstruct the quantum information. And that's the story. And just again, if you're a little bit disoriented by this geometry, you should think of these causal diamonds, which are supposed to be diamonds in space-time. They're supposed to be long and thin like this. And so the particle which is in the diamond at an early time might be over there, overlapping in one corner, and the particle at the late time is in the upper corner. These are just very boosted frames in the jargon of relativity. Now, I'd like to take it's helpful to look sort of just structurally at how we made this thing work. So we have 3 diamonds, D0, D1, D2, and there's a causal curve from diamond 1 to diamond 0, from diamond 0 to diamond 2, and diamond 2 to diamond 1. Right? This is my causal merry-go-round. You can sort of go in circles, sort of. And what made this work is that I had an error-correcting code such that if I collected, well, we should think each particle follows one of these red trajectories, right? So I want to make sure that in any one of these diamonds, there's enough information to reconstruct the information. So what do? Well, I look at diamond 1, and I see, well, diamond 1 has access to 2 out of the 3 of the shares of this code, right? And any 2 out of 3 is enough to reconstruct the information, like so. So if I design a code with 3 shares, one corresponding to each of these edges, such that if I collect any set of edges marked by my purple swaths, that's enough to reconstruct the information, then I will have succeeded in the task.
Don't you need to have 2 shares at the same time?
No, that's not the definition, right? Like the definition is that the information has to be localized in that region of space-time. So if you think about what I was saying before, it does mean that if you choose a particular time in the diamond, like that waste time when we actually are talking about essentially a sphere, then in that spherical region, you're going to have both of those particles. Now, if you wanted to operationalize this, what you could say is that if somebody made a request for the information at the base point...
So I understand that as the summoning task.
So you can convert this language into the summoning task. Okay. But, so I haven't said anything to you about how you would check, physically that this had actually been done. Like if someone wanted to build an experiment and convince you, right? It wouldn't be very convincing to say, well, I had some particles and I just set them around and I was done. Right? They want to do some measurements at the end of the day to confirm it. So you can operationalize this, quite effectively. But I just wanted to speak in abstract terms, like, is the information there? So here's a more complicated scenario. So now we have 4 diamonds, and the way that you should visualize this is that each of the diamonds is sitting on one of the faces of this cube. It doesn't really, the particular geometry doesn't matter. But if you wanted to try to determine, is it possible to replicate the information in this case, what I would do as a first step is I'd try to make sure that there's no violation of no cloning, right? Which would mean that there has to be a way to send a message from each of these diamonds to each of the others, or vice versa. And I'm not going to force you to check, but it turns out in this case, there is a way to send a message. Each of these pairs of diamonds is causally related. So there's no obvious violation of the no cloning theorem. So the next question would be to think, well, what other constraints might exist about how you'd replicate information? And the answer is there are none. So there's a theorem that each and every diamond in space-time can contain the same quantum information if and only if every pair is causally related. Right? So another way of stating that, each and every diamond can contain the same information. You can replicate it if and only if there is no really obvious violation of no cloning or causality. Right? So this is one of those results in physics where everything that is not sort of obviously forbidden is required. Well, I don't know if it's required, but it can be done. Okay. So what is the general procedure for making this work? Let's think about this, this particular example. We're going to encode our information into a quantum error correcting code. And there's going to be one edge, one share for every edge connecting the diamonds in the graph, where an edge represents a causal relationship. Right? So I can send it, if I look in my original graph of diamonds, for example, there's an edge, or I can send a message from the 0 diamond to the 1 diamond, right there. And so I draw a corresponding edge in this graph on the right. And because every pair of diamonds is causally related, every pair of diamonds in this graph is going to have an edge between them. And it might be an edge in one direction, another direction, it might be bidirectional, I don't care. I just need an edge. And if it's bidirectional, just choose one of the directions, I don't care which. So we're going to encode into a quantum error correcting code with one share for each edge. And the code property is going to be that the information can be recovered from, if I take all of the edges associated to a particular vertex. Okay, so for example, if I have the shares from this edge, and that edge, then I can recover the information because those are the 3 edges that touch vertex 3. And for this particular graph, there are going to be 4 different ways potentially to recover the information. And the procedure is just going to be that for each of those shares, I started at the base of the arrow. So for example, I could start a share for this edge up top in diamond 0, and then I just follow the causal trajectory up to diamond 1. Right? So then I just take that share and just move it through space-time along that causal curve. And that's permitted. And if I do that, then then enough shares to recover the information at diamond dj pass through dj, just by construction. And so that's what I need to do. Now for those of you who do know something about quantum information, this is actually an unusual and potentially disturbing quantum error correcting code, because if you count up the number of shares, there's 1 for each edge, right? So there's n choose 2 if there are n vertices. But the number of edges touching a particular vertex is n minus 1. Right? So you recover the information with n minus 1 out of n choose 2 shares, right? Which is roughly 1 over n shares. Right? Which means that with a vanishing fraction of the shares, you can recover the information. And if you think back to the no-cloning theorem, people who think about quantum error correcting codes usually think that the no-cloning theorem tells you that if you have a quantum error correcting code, you shouldn't be able to recover the information with fewer than half of your shares. Because then with the other shares, you could recover it again and get 2 copies. But the structure of this code is such that you don't violate the no-cloning theorem. I'll let you think about why. So now the new part for Prakash, how do you go find those codes? So this is the picture that we have. We're going to have, say, in this particular case, we're looking for a code with 6 shares, such that I can recover from either this 3, those 3, those 3, or those 3. Where do we find such codes? Well, we can redraw our graph as a tetrahedron, if we so desire. So why not? I've redrawn the graph as a tetrahedron. And as I said at the very beginning of the talk, we want to figure out, like in our original paper, the one that I guess Prakash has read, we figured out how to do this for qubits. But we like to do this for a continuous variable degree of freedom. And in a fairly simple way to try to encourage, so that we can have a proposal to convince an experimentalist to go and build such a thing. So we want to encode this in a continuous variable degree of freedom. So we're going to I just need a little bit of notation. We're going to have 6 shares. And so my Hilbert space is going to be L2 of R6. And I'm going to have certain unitary transformations in L2 of R6 that are going to be labeled by pairs of real numbers, or pairs of real vectors in R6. And so my unitary transformations of a pair of V and W are going to be the exponential of I times the dot product of Vj with a bunch of x operators, and the dot product of W with a bunch of p operators, translations in x, or generators of translations in x. And so these are my unitary operators. And the code is going to be a subspace of L2 of R6, defined by a subgroup of commuting operators. I'm almost done here. So the subspace is given by, or the subspace that I'm going to use to generate these unitaries is the span of things in the form V1, V2, V3, and W1, W2. And I think about the chain complex on this tetrahedron. And it so happens that if I choose my V's as some of the boundaries, and I choose my W's as co-boundaries, then these operators naturally satisfy the commutativity conditions that I need, and then you can go a little bit further and verify that it satisfies the error correction conditions. And this generalized arbitrary n and gives you a fairly simple structure for the code. So those are the ones we want to build. So I've just demonstrated to you that we can give a complete characterization of all the ways that information can be replicated in spacetime. And it's not just the trivial examples. There are actually some very interesting configurations of information replication. Similar ideas can be used to exclude information from certain regions, so you can talk about secret sharing, which was my ambition at the beginning until I realized it was a half-hour talk. And what next, as I said, what I really want to do is convince someone to build it, but we can also use this for cryptography and other things. So thanks for your attention.
So fascinating to see quantum error correction and something that looks like algebraic topology on the same slide. So that unitary that you had, what does it look like in terms of creation and compilation operators?
Oh, well, I mean,
Surely it would look simpler, you know?
I don't know if it looks simpler. I mean, I would have to, I'd have to just write out the definition of X and P in terms of A and A dagger.
That's not how you came up with it.
No, like these are the standard. These are kind of the standard generalizations of X and Z, right? If you're talking about qubits, right? That these are, I think these are called Weyl transformations in general. So yeah. So I think they're naturally phrased in terms of these quadratures like that. So I'd have to write it out to be sure, but I think it's more easily interpreted in this form. It's linear in A and A dagger. Very good. Yeah.
More questions?
So Prakash asked something earlier, and you said something about summoning.
Right.
But I suppose I didn't quite get that.
Oh, okay. Yeah.
With the simpler thing we started with, just with the two equilateral triangles.
Yeah.
Can you say anything about the sort of operational problem of actually recovering the information?
Yeah, exactly. So in this simple example, you could think of a game where this becomes adversarial. So I'm going to try to convince you that I am able to replicate this information. So what you're going to do is you're going to post your agents at these Y positions, and one of the agents is going to make a request for the information, but I don't know in advance which one it's going to be. Okay, so maybe at location Y0, or space-time location Y0, your agent is going to say, all right, show me the information, right? And so my agents can then go scurrying about in the future of Y0 to try to collect the information, right? And in particular, they can make it out to this point and collect the particle there and redirect it towards Z0, right? And so the information can be redirected towards Z0, and at Z0 you will also have agents, well, they can be the same ones, sitting there waiting to see if the information makes it there, right? And so if the information is located inside the causal diamond, you can get it to Z0, but if it's not, you're going to fail, or I could get it to Z0, otherwise I'm going to fail. And so that's that's how you operationalize this. And it was Adrian Kent who first talked about this task that he calls summoning, which is essentially the sort of the operational version of this question.
So these two can do that. On the next one, we had the simple error. Yeah, there's 2-3 error correcting code. So if we think of Y2 and Z2, that's just one of these sort of narrow diamonds, I guess.
Yeah, exactly.
Presumably, normally when you're doing this code, to recover it from two particles, you need to do some entangled measurements on them?
Yes.
I'm guessing?
Yeah.
So what this guy, it seems, would have to do, I mean, he's got the one of those two at Y2, and the other
one
at
at
Z2.
Z2.
So it sort of looks like he has to do an entangled measurement across time on those two.
No,
so maybe he can do, but it's not sort of obvious to.
Yeah. So the way that it will be done, again, imagine you're the skeptic. So you have your agents at Y0, Y2, and Y1, and then you say, all right, I'm at Y2. I want to see if the information, demonstrate to me that the information is available in diamond 2. So what I will do, there's a particle sitting at Y2, right? So instead of sending it along the red trajectory, I'll redirect it towards Z2, right? Because the particle's sitting there, so that's my choice, right? So the particle that was at y2, I'll redirect it towards z2, and the particle that was at y0 is just by default going to follow the trajectory towards z2. So then two particles will appear at z2, and then that measurement can be performed there. Does that make sense?
Yeah.
Yeah. So that's what you do in general. That there could be some fairly complicated procedure required to do the verification, but you as the verifier, I will hand you all the quantum information, and then you can perform the computation that I direct at that point.
So is the idea is this summoning then always sort of possible? If you're
It's always possible.
The case that the information is in each.
Yeah, provided that condition is satisfied, that every pair of diamonds is causally related, then it's always possible. And I'm not sure about the computational complexity of the decoding. I haven't thought about that too much.
Sorry, we don't have the time to take more questions. Thanks.